The polarity of molecules plays a tremendously important role in the discussion of intermolecular forces. And intermolecular forces are forces that, as the name implies, hold molecules together. Now, if you recall our discussion of ionic bond when we talk about molecules such as sodium chloride, we mentioned that the positively charged sodium anion and a negatively charged chloride anion attract each other very strongly. And this explains the stability of the crystal lattice of sodium chloride. Well, the same thing applies to molecules which have a little bit less charge than sodium and chloride in this. For example, formaldehyde has a delta plus charge on carbon and a delta minus charge on oxygen. And although in absolute values these charges are much smaller than the fully positive charge on sodium and the fully negative charges on chlorine, they're still charges. And so if we imagine another molecule of formaldehyde, we can envision that there will be some attraction between delta minus on one oxygen and delta plus on carbon, and between these pairs of atoms. And this is an example of an intermolecular force. And although it seems like a very subtle effect, intermolecular forces are actually the thing that holds all the solids and liquids together and also heavily influences their properties such as solubility. There are three main types of intermolecular forces we'll talk about. The first one are the so-called dipole-dipole forces. And they occur in polar molecules. So this is a limited subset of molecules because not all molecules are polar. The second type are the London dispersion forces, which occur in all molecules. So they are very general. And finally, a sort of a specific type of dipole-dipole forces, which is very common, is the hydrogen bonding. Which occurs in molecules with OH or NH bonds. So in molecules where there is an electronegative atom bound to hydrogen. Let's talk a little bit about all three of these types of interactions. And the first one we'll talk about are the dipole-dipole interactions. And if you look at a molecule with some sort of a permanent dipole, and one of those that we talked about recently is chloromethane, then the positive end of this dipole is on carbon and the negative end is on chlorine. And if you orient another molecule of chloroethane analogously, then we will again have the same dipole, and the positive ends of one dipole will attract with the negative end of another, this way. A simplified way to represent this interaction would be this, and since the opposite charges are immediately next to each other, this is an overall attractive interaction. Of course, if the molecules approach each other in what we call a wrong orientation, then they can put their negative ends next to each other or their positive ends next to each other. And either one of these two orientations will be repulsive, which basically explains why these things don't happen so much. Because as soon as molecules start approaching each other in the orientation is potentially repulsive, they repel each other and reorient until eventually they assemble into a mutually attractive orientation. And this is, of course, dipole-dipole force, so it's requisite on the existence of permanent dipoles. But the so-called London dispersion forces are not. They basically are observed in any kind of a molecule. For example, molecule which is completely nonpolar, CCl4, has a dipole of 0, but its boiling point is 77 degrees, which means that this is relatively high boiling point, which means that the molecules in the liquids hold each other together relatively strongly. For comparison, the chloromethane, the chloroform molecule with a strong dipole of 1.10 dBi, has a lower boiling point of just 62 degrees. So why is this? Well, it turns out that even though tetrachloromethane has no permanent dipole moment, the electronic charge in that molecule is never really constant. It always fluctuates a little bit. And so there is such a thing as an induced dipole with a tiny positive and negative charges which are distributed along this molecule. Once the next molecule approaches this molecule, the influence of the first molecule causes a distribution of positive and negative charges in the second molecule as well. And it causes the redistribution which will correspond to an overall attraction. In other words, one molecule has a slight variation in negative charge, and the other molecule, once it sees the negative charge of this first molecule, will orient its positive charge towards it, resulting in an attraction. These forces are very weak and they drop off very quickly with distance, but they're proportional to the surface area of the molecule. So the longer the molecule, the more surface attraction will be between these induced dipoles on one end and induced dipoles on the other end of different molecules. And since these forces are proportional to surface, and this is an important point, that allows us to first say that bigger molecules attract each other more strongly. And secondly, that spherical molecules attract each other weaker than linear ones. And the reason for this lies in the fact that the contact surface is really the most important point here. And if we think about, for example, when you go to a supermarket and buy a carton of eggs, you notice that eggs are roughly spherical in shape, and the carton is largely empty space because spheres are difficult to pack next to each other because there's a lot of empty space. On the other hand, if you buy a box of a big box of cereal with still 6 smaller boxes of cereal which are rectangular, they're packed without really any empty space between them. And the same applies to molecules. So if you look at an example where we have this pentane, its boiling point is 36 degrees, and this is a linear molecule. The same molecule, same number of carbons, but different isomer, with a branch has a boiling point of just 28 degrees. If you introduce a 2 branch, and now we have this molecule which is roughly spherical, the boiling point here is just 10 degrees, even though the molecular formula overall is the same. So London dispersion forces are another very important type of intermolecular forces, and the final one we'll talk about will be hydrogen bonding. And as I mentioned, hydrogen bonding is a strong dipole-dipole interaction, nothing more than that. However, it is a pretty specific interaction because it needs a hydrogen bonded to electronegative element. Electronegative elements in this context are things like NH and OH. Of course, FH, also hydrofluoric acid, and HCl are also hydrogen bonds, but since they're not organic molecules, we don't really talk about it. Or if you look at a molecule with a hydrogen bond, such as methanol, which satisfies all of these requirements, then we'll notice that the free electron pair of oxygen coordinates a hydrogen from another molecule, resulting in sort of a shared arrangement of this hydrogen between two different oxygens. Okay? And these bonds are crucial in nature, and they raise boiling points significantly. For example, if you look at ethanol, boiling point of this is plus 78 degrees centigrade. But if you look at an isomer, which just has this oxygen moved in the middle, the boiling point here is minus 25 degrees. So this is different of about 100 degrees, and this is solely a consequence of hydrogen bonding, since this molecule, known as dimethyl ether, has no hydrogens directly bound to an electronegative element. The strength of this bond is much smaller than a covalent bond, but it's still significant. So this is the hydrogen bond. It's about 5 kcal per mole. But if you just look at normal covalent hydrogen-oxygen bond, this is about 100 kcal per mole. So it's about 20 times stronger. But still, the hydrogen bond is not negligible. Now this applies, the molecules I've just shown is an alcohol. This also applies in amines. So if we have a molecule such as trimethylamine, this has a very low boiling point of 3.5 degrees centigrade because there are no hydrogens here. So there is nothing to hydrogen bond. But if we now have one hydrogen which is directly bound to nitrogen, this hydrogen is able to engage in hydrogen bonding, and the boiling point rises to about 37 degrees. If we have two hydrogens, the effect that are directly bound to nitrogen, the effect becomes even greater, so the boiling point now is 49 degrees centigrade. The presence of hydrogen bonding is very important in nature. Proteins and DNA molecules are extensively hydrogen bound to itself, as well to the water which surrounds them. And actually perhaps the most singular, most important effect of hydrogen bonding in nature is the structure of water. So water is a very small molecule, so the molecular weight of water is only 18 grams per mole. But still, it's a liquid and boils at 100 degrees centigrade. If you contrast that to something like CO, which has a molecular weight of 28 grams per mole, so much larger, this is a gas, and its boiling point is, I don't know exactly, but it's probably somewhere around minus 100 degrees. And so this huge difference is caused solely by the water's extraordinary ability, because it has a very large ratio of hydrogen to oxygen, to extensively hydrogen bind. And you can just start to imagine what would happen if water was a gas. It would be a weak gas, it would be entirely in atmosphere, there would be no oceans, and if you know that life developed in oceans, it's really questionable whether the life in the form we're knowing now could exist without hydrogen bond. So this is a singular most important effect, but we'll talk about other effects that are relevant to the small organic molecules we're going to study, such as solubility, in the next topic.